Have you ever looked up at the night sky and wondered where it all ends? The universe doesn't have an edge in the way you might imagine. Instead, it's like an inflating balloon with galaxies moving apart but no true center. What we can observe is limited by how far light has traveled, meaning the universe's edge isn't a wall, but a horizon we can't yet see beyond. Tonight, let's drift into the mystery of cosmic boundaries, where space stretches further than our minds can fathom. Welcome back to The Sleepy Scientist, where we explore the universe one quiet question at a time. Before we drift deeper, tell me, where in the world are you watching from? Drop a comment with your name, your city, and whether it's dawn, dusk, or deep night there. Let's see who's gathered here under the same sky tonight. No need to rush, just get comfortable and let the wonder unfold slowly. Ready? Let's begin. Take a balloon and cover it with tiny dots, not just a few hundred evenly spaced across the surface. Now blow it up slowly. Watch how every dot moves away from every other dot. That's your universe. Not the air inside, not the rubber, just the stretching surface where all those dots live. Here's the first strange thing. No dot is special. Pick any you like and watch its neighbors retreat. From that dot's perspective, it's the center of the expansion. Here's the twist. Every sees the same thing. The balloon's surface has no true center, no privileged point where the expansion begins. The universe works the same way. Galaxies act like those dots. Through telescopes, we see them all moving apart, not from some central location, but from everywhere at once. A galaxy, 1,000,000 light-years away, moves slower than 1/2 million light-years distant, following the same pattern as dots on our balloon. The farther apart two galaxies are, the faster space stretches between them. This balloon analogy captures cosmic expansion beautifully. But it falters when we try to imagine where the center might be. Our human brains crave reference points, instinctively search for the spot where the stretching began, some anchor in the cosmic ocean, but the universe refuses to cooperate. The Big Bang happened everywhere simultaneously, not at a single point, but across all space at once. Space itself expands, carrying galaxies along like raisins in rising dough. A raisin near the edge of the dough doesn't experience expansion differently from one near the middle. Neither does a galaxy at the edge of the observable universe, a concept we'll soon unpack. This realization unsettles and exhilarates. It means Earth holds no special cosmic real estate. Our galaxy drifts along like all the others, riding the stretching fabric of space-time without a fixed center to measure against. Even if we could travel instantly to some imagined outer edge, we'd find more galaxies retreating in every direction, just as they do here. What we call the observable universe, the portion of space from which light has had time to reach. As functions like a horizon at sea. Sail toward it, and it recedes. The actual universe likely extends far beyond what we'll ever see. The balloon analogy also helps explain why we can't detect the expansion locally. In our solar system, gravity binds planets and stars too tightly for space-time stretching to overcome. Only across vast intergalactic distances does expansion dominate over gravity's pull. Now imagine the balloon's surface is invisible. All we see are the dots. Could we still deduce the balloon's shape? Astronomers face this challenge daily. It's mapping the universe's large-scale structure while embedded within it. No physical edge exists in this expanding cosmic fabric. No boundary wall, no abrupt cutoff. It's just an infinite or near-infinite stretch of space-time, growing ever more diffuse as distances increase. Trying to locate the universe's center proves as fruitless as searching for the center of Earth's surface. This realization carries profound implications. It means every point in cosmic history has an equal claim to being central. The hydrogen atoms currently inside your body once occupied a position indistinguishable from the rest of the primordial universe. As the balloon expands, dot-to-dot distances grow, but the dots themselves don't stretch. Similarly, galaxies remain coherent objects because electromagnetic forces within them dwarf cosmic expansion's local effects. Yet given enough time, even galaxy clusters may stretch apart. Consider this. If we could watch cosmic expansion in reverse, We wouldn't see everything crunched to a single point like in movies. Instead, the density would increase everywhere uniformly, like dots crowding together across the entire balloon as it deflates. The balloon model remains can't show how three-dimensional space expands in all directions, but it illustrates key principles. When cosmologists say the universe expands, it means space itself grows between galaxies. It's not that galaxies fly apart through static space. This distinction matters profoundly. If galaxies move through space, they'd have measurable motion. Relative to some background, space lacks any absolute reference frame and insight dating back to Einstein. Only relative motion between objects holds physical meaning. Now imagine the balloon keeps expanding forever. Some dots move so far apart that light from one could never reach another. This scenario mirrors what may await our actual universe on cosmic timescales. Astronomers measure expansion rates using standard candles objects of known brightness. By comparing apparent brightness with actual brightness, they calculate distances. These measurements reveal not just how fast space stretches now, but how that rate changed over billions of years. The balloon analogy's greatest strength lies in divorcing cosmic expansion from human intuitions about motion. It demonstrates how something can grow without expanding into anything, how every location can seem central while none truly is. Yet even this simple model challenges our imaginations. The expanding balloon exists in our three-dimensional world. While the universe's expansion requires no external dimension to expand into, the math works whether or not higher dimensions exist. This leads to a startling thought. If the universe had an edge, what would lie beyond? More space? Nothing? These questions may lack meaning because the universe could be self-contained. It's finite yet unbounded, like the balloon's surface extended to higher dimensions. As we move beyond analogies into observable evidence, becomes clear the cosmic expansion we've measured represents just the latest chapter in a far stranger story, one written in redshifted light from ancient galaxies racing away faster than we'd ever imagined possible. Here's the universe. You can see right now. But here's the catch, it's not the whole universe. It's just the part where light has had enough time to reach us. The rest might as well be a blank space on the map, not because it isn't there, but because its light hasn't arrived yet. Think of it like sitting by a campfire at night. The light from the flames illuminates a circle around you, but beyond that, the forest is dark. Not because the forest ends, just because the firelight hasn't traveled far enough to show it. It's the observable universe works the same way. We're surrounded by a sphere of visibility, about 93 billion light-years across. And beyond that, the cosmos fades into mystery. Now here's where it gets interesting. Light doesn't just show us where things are, it shows us when they were. Every photon that hits your eye is a little time traveler carrying a story from the past. When you look at the stars, you're not seeing them as they are right now. You're seeing them as they were years, centuries, even billions of years ago. The further away something is, it's the further back in time you're peering. The James Webb Space Telescope takes this to the extreme. When it captures light from galaxies like GNZ11, one of the most distant we've ever observed, it's receiving photons that left that galaxy over 13 billion years ago. That galaxy, as we see it, is an infant, a glimpse into the universe's toddler phase. But here's the catch. GNZ11 isn't still a toddler. It's had billions of years to grow and change since then. We just can't see its present yet because that light is still on its way. This creates a strange limit to our knowledge. No matter how powerful our telescopes get, we'll never see past a certain point. Not because space itself stops, but because the light from beyond hasn't reached us. And there's a chance it never will. The universe is expanding so fast that some regions are already slipping away faster than light can bridge the gap. Their stories will never reach us. In a way, we're all stuck in a cosmic version of Groundhog Day, receiving messages from the past, but never the present. So when we talk about an edge to the universe, we're really talking about the edge of what we can perceive. A horizon, just like the one that hides distant ships at sea, where the curve of the earth takes them out of sight. This horizon isn't static either. As time passes, more light arrives, pushing the boundary slightly further. But even as new galaxies swim into view, the expansion of space is carrying others away forever. It's a race between light struggling to reach us and the universe stretching the distance even wider. That leads to something humbling. There's a whole universe beyond what we can, regions where stars and galaxies might look entirely different from what we know. But unless we find a way to outpace light itself, those places will stay hidden from us. So the edge isn't really an edge at all. It's just the limit of our vision,
out there,
a horizon
in the
that dark
shifts
beyond the
with time.
light. The universe keeps going. Just can't see it yet. Now, think about what this means for cosmic time. If every glance at the stars is a look into the past, what happens if we look far enough? Back? Could we witness the very beginning? When you look up at the night sky, you're never seeing the universe as it is right now. Those pinpricks of light have traveled across space for years, decades, even billions of years before reaching your eyes. The Andromeda Galaxy, you might spot it on a clear night. That fuzzy patch shows how it looked 2.5 million years ago when light first began its journey toward Earth. Astronomy gives us a unique kind of time machine. Because light takes time to travel, every distant object we observe is essentially a snapshot from the past. The further away something is, the older the image we receive. This means when astronomers study the most distant galaxies, they're peering back to when the universe was young. Take GNZ11, currently the farthest known galaxy. Its light has traveled 13.4 billion years to reach us, showing the galaxy as it existed just 400 million years after the Big Bang. Compare that to Andromeda. While both appear in our sky tonight, one shows a relatively nearby neighbor, as it was when early humans were discovering fire, while the other reveals the universe in its infancy. There's a natural question that follows. Could we look far enough to actually see the Big Bang itself? In theory, yes, but in practice, it can. The earliest light we can observe is the cosmic microwave background radiation, essentially the afterglow of the Big Bang from about 380,000 years after the event. Before that, the universe was too dense and hot for light to travel. Free light was like trying to see through thick fog. Imagine. The universe's history is a movie reel where each frame captures a different era. The farthest galaxies show us the opening scenes. The cosmic microwave background reveals the opening credits. But the very first moments remain missing footage. We can reconstruct parts of the story through physics and mathematics. But some frames may be lost forever to the intense conditions of the early universe. This time travel aspect of astronomy helps explain why telescopes act like time machines. The Hubble Space Telescope's deep field images, which revealed thousands of galaxies in what seemed space, showed us the universe as it was billions of years ago. The James Webb Space Telescope pushes even further back, capturing galaxies forming in the cosmic dawn. Each new instrument lets us scroll further back through the universe's photo album. There's something profound about realizing we're all time travelers when we gaze upward. The light hitting your retina tonight from distant stars began its journey. Before human civilization existed, before the dinosaurs roamed, before Earth had even formed. In that sense, astronomy connects us directly to events that happened in the unimaginably distant past. But as we'll see next, this backward glance through time also reveals something strange happening to the universe right now, something that might determine everything that comes after. The expansion we observe in the distant past isn't behaving as expected. Instead of slowing down, the universe's expansion seems to be speeding up. Some unknown force appears to be working against gravity, pushing everything apart faster and faster. We call it dark energy, and it's the next piece of our cosmic puzzle. In 1998, astronomers made a discovery that flipped our understanding of the universe upside down. They were studying distant supernovae, those brilliant stellar explosions we talked about earlier, when they noticed something strange. These cosmic beacons appeared dimmer than they should have been based on their distance. The implication was startling. The expansion of the universe wasn't slowing down as everyone expected. It was speeding up. Imagine throwing a ball straight up in the air. You'd expect it to slow down as gravity pulls it back toward Earth. But what if instead of slowing, the ball started moving faster and faster, racing away from you? That's essentially what astronomers found happening with the entire universe. Galaxies aren't just drifting apart, they're accelerating away from each other at an increasing rate. This finding was so unexpected that scientists initially doubted their own measurements. The teams involved, the Supernova Cosmology Project, and the High-Z Supernova Search Team, independently verified their results multiple times before announcing them. Even then, many astronomers remained skeptical. But subsequent observations have only confirmed this discovery, which eventually earned the team leaders the 2011 Nobel Prize in Physics. What could cause this cosmic acceleration? Scientists call it dark energy, though that name tells us more about what we don't know than what we do. The term dark here simply means unknown, not literally dark or evil. There are two leading theories about what dark energy might be. Both come with their own set of mind-bending implications. The first possibility connects back to Einstein's cosmological constant, a term he originally included in his equations, to keep the universe static, which he later called his greatest blunder when expansion was discovered. Turns out he might have been right after all, just early. This version of dark energy would be a property of space itself, the energy of empty vacuum, maintaining constant density even as the universe expands. The second theory suggests dark energy might be some sort of dynamic field permeating space, much like the Higgs field gives particles mass. This version could change over time, potentially leading to different cosmic futures than the cosmological constant would predict. It might be related to quantum fluctuations or some undiscovered interaction we don't yet understand. Here's the humbling part. Despite years of study, we still don't know which, if either, of these explanations is correct. Dark energy makes up about 68% of the total energy budget of the universe, yet we can't detect it directly. We only infer its existence through its gravitational effects on the universe's expansion. It's as if you noticed all the furniture and your house was moving around at night, but couldn't actually see who or what was moving it. Scientists have proposed various ways to probe dark energy's nature. Future telescopes could measure how the expansion rate changes more precisely over time. Others might look for subtle distortions in the cosmic microwave background that could reveal dark energy's properties. But for now, it remains the biggest unsolved puzzle in cosmology. The mystery becomes even more profound when we realize dark energy's influence hasn't always been the same. In the early universe, gravity dominated everything. Matter was packed so densely that expansion slowed down. Then, about 5 billion years ago, dark energy took over as the universe became more spread out. Now, it controls the cosmic show, stretching space-time at an increasing rate. Some theorists speculate that dark energy might be connected to other fundamental mysteries, like quantum gravity or the nature of time itself. Others wonder if it could relate to multiple universes in some greater multiverse. But these are speculations without evidence. The simple truth: we're still at the we know it's there but don't know what it is stage of understanding. This uncertainty doesn't frustrate most cosmologists, it excites them. Dark energy represents a fundamental gap in our understanding of physics, pointing to either new physics beyond our current theories or a radical reinterpretation of existing ones. As astronomer Alex Filipenko has put it, the most exciting discoveries are the ones you don't expect, the ones that shake things up. Whatever dark energy turns out to be, its implications for the universe's fate are profound. If the acceleration continues unchecked, trillions of years in the future, distant galaxies will disappear beyond our horizon as the space between us expands faster than light can cross it. The observable universe will shrink rather than grow, leaving future civilizations with a much darker, emptier sky. But that's getting ahead of ourselves. For now, dark energy remains out there, invisible and enigmatic, constantly reshaping the cosmos in ways we're only beginning to understand. Its discovery reminds us how much we still have to learn about even the most basic workings of the universe. We call home, the universe will end. That much seems certain, but how? Science offers two dramatic possibilities, each with its own bleak poetry. One ends in fire, the other in ice. Centuries before scientists seriously considered the question, poet Robert Frost imagined these cosmic alternatives, whether the world would perish in flames or freeze in endless cold. Today's cosmology suggests he might have been more right than he knew. The fiery scenario is called the Big Crunch. Picture the expansion of the universe reversing. After billions of years flying apart, galaxies begin falling back together. Space itself contracts, growing denser and hotter. Temperatures skyrocket as everything converges toward a single point, a mirror image of the Big Bang but played in reverse. Stars collide more frequently as the universe shrinks. Eventually, all matter compresses into an ultra-dense state, perhaps triggering another cosmic rebirth. It's the cyclical universe theory, one grand cycle of expansion and contraction after another. Then there's the icy alternative, heat death. In this scenario, the universe keeps expanding forever. Galaxies drift apart until the space between them becomes unimaginably vast. Star formation gradually stops as gas clouds become too diffuse. Black holes Existing stars burn out through Hawking radiation. Eventually, the universe reaches maximum entropy, complete thermodynamic equilibrium. No more heat flows because everything is the same temperature, barely above absolute zero. Atoms themselves may decay, leaving behind only a thin soup of subatomic particles and radiation, evenly distributed across an ever-growing void. Current evidence strongly favors the cold ending. Those distant supernova measurements that revealed accelerating expansion. They suggest dark energy will keep pushing galaxies apart at an ever-increasing rate. There's no sign of gravity winning the tug-of-war. Unless dark energy behaves differently in the future, and we have no reason to think it will, the universe seems headed toward the cold, oblivion of heat death rather than a fiery crunch. But cosmic endings are tricky to predict. The science of thermodynamics tells us that in any closed system like the universe, entropy must increase over time. Energy disperses, becoming less useful for doing work. Differences in temperature even out. It's like a cup of coffee left on the counter regardless of how hot it starts. Eventually it reaches room temperature and stays there. The universe appears to be doing the same thing on an unimaginable timescale. Some calculations estimate this final state would occur around 10,100 years in the future. That's a 1 followed by 100 zeros. At that point, protons themselves might decay, breaking down matter at the most fundamental level. If that happens, even black holes won't last forever. They'll slowly leak away their mass as Hawking radiation over inconceivably long timescales. The last light in the universe may come from evaporating black holes, faint and cold as they dissipate into nothingness. The Big Crunch scenario isn't completely ruled out, though. Some models suggest dark energy's strength could change over time. If it weakened enough, gravity might eventually regain the upper hand, pulling everything back together. Other theories propose that what we call dark energy might actually indicate our understanding of gravity is incomplete at cosmic scales. Einstein's theory of relativity needs modification for the universe as a whole. Perhaps the expansion could reverse someday. There's also the Big Rip variant, a particularly violent ending where dark energy's strength increases over time. In this scenario, the universe wouldn't just expand, but would tear itself apart at every scale. Galaxies would shred first, then solar systems, then planets, finally ripping atoms themselves to pieces in a catastrophic finale. Current observations don't support this version, but it remains a mathematical possibility based on certain dark energy models. Astronomer Alex Filipenko often frames this cosmological debate in Frostian terms. Will the universe end with a bang or a whimper? He asks, noting how current evidence points toward the whimper of heat death rather than the bang of a crunch. But he acknowledges we might never know for certain. So vast compared to human existence that the ultimate fate may remain forever in the realm of theory rather than observation. Entropy provides silent testimony for the cold ending. Everywhere we look, we see energy dispersing and systems becoming more disordered. Stars burn out, galaxies grow dim. Even black holes, those cosmic vacuum cleaners, slowly lose mass. The arrow of time points irrevocably toward greater entropy, a universe growing cold and dilute rather than hot and dense. Particle physics suggests protons may eventually decay, erasing the building blocks of matter itself over sufficiently long periods. Interestingly, these cosmic endings aren't just distant possibilities, they influence the universe's evolution right now. The presence of dark energy already determines how galaxies form and separate. If we lived in a universe destined for a big crunch, structures would be forming and interacting differently. The very fact that we observe accelerating expansion tells us something profound about the universe's long-term trajectory. Each scenario carries its own existential weight. A cyclical universe offers the cold comfort that something might come after the end. Heat death presents a more conclusive conclusion, an eternal stillness where no new stories can be told. In some ways, the cold ending seems lonelier, at least in the big crunch scenario. Everything goes out together in a spectacular finale. We might never witness the final act ourselves. Even if intelligent life somehow persists for billions of lifetimes, the universe's fate unfolds over timescales that dwarf biological existence. By the time heat death approaches, any remaining civilizations would face an energy crisis of cosmic proportions, desperately trying to extract useful work from an increasingly uniform energy landscape. Perhaps the most humbling realization is that even if we perfectly understood dark energy's nature today, predicting the ultimate fate could still be impossible. The universe might contain phenomena we haven't discovered yet that could change everything. Our models rely on physics as we know it, but physics as we know it might be incomplete. For now, we're left with observations that strongly suggest a cold, quiet ending. Stars will blink out one by one. Space will grow vast and empty. The cosmic background radiation will redshift to undetectability. The universe appears headed not toward fire, but toward the deepest cold imaginable. And yet, against this cosmic backdrop, something remarkable is happening today on one small planet. Tiny collections of atoms have arranged themselves in ways that can ponder these very questions, which leads us to perhaps the most astonishing realization of all. The atoms in your hands, right now, have traveled billions of years across space to get here. The hydrogen in your body dates back to the Big Bang itself. The heavier elements, carbon in your cells, the iron in your blood, the calcium in your bones, were forged in the hearts of dying stars. Every breath you take contains oxygen atoms that have spent millennia drifting through interstellar space before becoming part of Earth's atmosphere when the universe began. Only the simplest elements existed, mostly hydrogen and helium with traces of lithium. The first stars formed from this pristine material. These massive stars lived fast and died young. In their cores, nuclear fusion created heavier elements up to iron. When these stars exploded as supernova, their violent deaths produced gold, silver, uranium, nearly every element on the periodic table heavier than iron. The explosions scattered these newly minted atoms across space, where they eventually became part of later generations of stars and planets. Our solar system formed. From a cloud of gas and dust enriched by multiple generations of stars, meteorites that fall to Earth contain tiny grains of stardust, actual, solid pieces of ancient stars that predate our sun. Your body contains about 20 milligrams of this stardust right now. The gold in jewelry or electronic devices likely came from colliding neutron stars, one of the most energetic events in the universe. The phosphorus in your DNA might have formed in the outer layers of red giant stars. This raises a question. How rare is Earth's particular mix of elements? The cosmic abundances show hydrogen and helium dominate together. They make up about 98% of ordinary matter in the universe. Oxygen runs a distant third, followed by carbon, neon, and nitrogen. Iron is surprisingly common for a heavy element. Some elements like gold and platinum are genuinely scarce. A single neutron star collision might produce enough heavy elements to seed entire galaxies. The periodic table becomes a cosmic history book. When you know how to read it, elements lighter than iron typically form in stars through fusion. Heavier elements require more extreme conditions, supernova explosions, or neutron star mergers. Some unstable elements like technetium exist only briefly in labs or dying stars. The very pattern of elemental abundances tells the story of cosmic chemistry over billions of years. Carl Sagan famously said, we are a way for the universe to know itself. The atoms that form your body were once part of stars and interstellar clouds. The same processes that shaped galaxies and planets also assembled the molecules that make up your cells. This connection isn't poetry, it's physics. Your body constantly exchanges atoms with the environment. The nitrogen you exhale today might become part of a tree next year. Stellar nucleosynthesis, the process by which stars create elements, follows precise physical laws. In a main sequence star like our Sun, hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. The very largest stars can fuse elements up to iron in their cores. Each step releases less energy until iron, which absorbs energy when fused. This is why iron-rich cores mark the death knell for massive stars when fusion can no longer provide outward pressure. The star collapses and explodes. Supernovae are element factories. The intense heat and pressure during these explosions can produce elements heavier than iron through rapid neutron capture, the R process. A single supernova can briefly outshine its entire galaxy while spewing newly synthesized elements into space. These atoms eventually mix with interstellar gas clouds, becoming raw material for new stars and planets. The accumulated products of countless such explosions. Modern technology lets us detect specific elements in distant stars and galaxies. Spectroscopy splits starlight into rainbows that reveal absorption lines, chemical fingerprints of elements. We found stars with unusually high amounts of certain elements, showing how stellar chemistry varies across the cosmos. Some ancient stars contain almost no heavy elements at all, relics from when the universe was young. The atoms in your body carry this history. The oxygen you breathe likely passed through multiple stars before reaching Earth. The iron in your blood probably formed in a supernova that exploded before our solar system existed. Even radioactive elements like uranium tell a story there. Decay rates act as cosmic clocks that help us date events in the early solar system. This cosmic genealogy makes Earth's life story even more remarkable. Our planet's particular mix of elements exists in delicate balance. Too much uranium would make the surface radioactive. Too little carbon would prevent complex chemistry. The right amounts of silicon, oxygen, and metals built a planet with continents and oceans. Without generations of stars living and dying to enrich the cosmos, rocky planets like Earth might not exist at all. Consider how many cosmic events had to happen just right to create the atoms around you. Stars had to form from primordial hydrogen and helium. Those stars had to synthesize heavier elements through fusion. The stars had to die in ways that scattered these elements into space. Later generations of stars had to form from these enriched clouds. Our solar system had to coalesce with the right mix of volatile and refractory materials to build a life-bearing planet. The odds seem staggering. Yet here we are on a planet that somehow collected just the right ingredients from billions of years of stellar alchemy. Other planetary systems have different chemical compositions, some richer in carbon, others in oxygen or metals. We found planets where it might rain molten iron or where the crust could be made of diamond. Earth's particular chemistry appears finely tuned for life as we know it. This leads to an unsettling thought. If we're made of star stuff, what does that say about our place in the cosmos? Our atoms were forged in the fiery cores of stars, yet here they've somehow become aware of their own origins. The universe has developed the capacity to study itself through beings composed of its own recycled material. The scientific version of this story differs from ancient creation myths, but retains a sense of wonder. Instead of being fashioned from clay or the body of a cosmic giant, we're literally assembled from pieces of exploded stars. The calcium in your teeth, the zinc in your enzymes, the sodium that carries nerve impulses, all these trace back to astrophysical processes that had no intent or purpose, yet somehow produced creatures capable of understanding them. Perhaps the strangest realization is temporal. Some atoms in your body may be billions of years older than others. The hydrogen could be primordial, while the iodine in your thyroid might have formed mere hundreds of millions of years ago in a stellar explosion. You're literally built from artifacts of different cosmic eras, all temporarily assembled into a thinking organism. This material connection raises profound questions. If we're the universe observing itself, what does that mean about consciousness? Are we a statistical inevitability given enough time and the right conditions, or an incredibly unlikely accident? The elements don't care either way they follow. Physical laws, whether anyone observes them or not. But here we are. Collections of atoms that can trace their lineage back to the birth of stars and wonder what it means. As we consider our place in this cosmic story, another question emerges. Among all these atoms arranged just so to make a thinking being, what does it mean that we can even ask whether we're special or insignificant? The universe has grown vast and complex enough to produce creatures that debate their own importance within it. Far from making us feel small, this cosmic perspective might instead suggest how remarkable it is that the universe has generated anything capable of understanding it at all. And that leads us to wonder, does the universe have a purpose? Or are we imposing patterns that don't exist? Here we are, a speck orbiting an ordinary star in an unremarkable galaxy, asking questions about the edge of the universe. It's strange when you think about it, this collection of atoms, called humanity, has developed the ability to contemplate its own origins. The anthropic principle suggests our existence as observers requires the universe to have certain properties. But does that make us special or just lucky? Take the pale blue dot image from Voyager 1. That photo shows Earth as a single pixel suspended in a sunbeam, taken from beyond Neptune's orbit. In that frame, every human who ever lived fits into a speck smaller than a camera sensor's grain of light, yet here we are on that pixel, mapping the same universe that appears to dwarf us. Astronomer Alex Filipenko describes humans as perhaps the universe's way of becoming conscious of itself. It's a poetic thought that the cosmos might need observers to give it meaning, but the numbers work against human exceptionalism. With billions of galaxies, each containing billions of stars, it's statistically likely that other intelligent species exist somewhere. Even if life is rare, the universe is so vast that rare could still mean millions of civilizations. On the other hand, filters like nuclear war or environmental collapse might prevent most civilizations from reaching our stage. We have no data either way, just probabilities and guesswork. The cosmic perspective flattens human drama yet magnifies our achievements. All wars, art, love affairs, and scientific discoveries have occurred on that pale blue dot. The same universe that could render us insignificant by scale makes our curiosity extraordinary by contrast. That we've decoded cosmic expansion, measured the age of stars, and traced our atomic lineage seems remarkable. Against the backdrop of infinite space, consider how recent our cosmic understanding is. 100 years ago, we didn't know galaxies existed beyond the Milky Way. 200 years ago, the age of the Earth was hotly debated. Ancient astronomers mapped stars without knowing what they were. Our present knowledge that we're made of stardust in an expanding universe represents a blink in cosmic time. Perhaps future civilizations will know answers to questions we haven't even thought to ask. This raises uncomfortable questions about purpose. If the universe will eventually experience heat death, what does anything matter? Purpose may work differently at cosmic scales. The joy of discovery, the drive to understand these, might be purpose enough. As Filipenko puts it, we're the universe's consciousness. It's a way of making sense of itself. The story isn't made meaningful by its ending, but by the telling. Science. Fiction often portrays first contact with aliens as humanity's great awakening. Cosmic perspective suggests we've already had that moment, not by meeting others, but by realizing our connection to everything around us. When we study distant galaxies, we're examining our extended family. The iron in their stars and our blood shares a common origin. This kinship with the cosmos runs deeper than biology. The Hubble Space Telescope captured an image called the ultra-deep field by staring at the empty sky for days. It revealed thousands of galaxies in an area smaller than a grain of sand held. At arm's length, each galaxy contains billions of stars. The sheer scale could make one feel small, but alternatively, it reveals how much we've learned to perceive. That empty patch of sky wasn't empty at all. We just needed the right tools to see what was there. humanity's place in the cosmos might resemble that ultra-deep field. What seems like emptiness might contain depth we can't yet perceive. Our current knowledge could be the equivalent of ancient astronomers seeing points of light without understanding their nature. Perhaps future breakthroughs will reveal connections we can't imagine yet, a cosmic web more intricate than we've dared hypothesize. The tension between feeling special and insignificant resolves oddly in practice. Learning we're made of stardust doesn't diminish us, it connects us. Realizing Earth is a tiny planet around an average star doesn't make home less precious. It makes the universe more hospitable. The cosmic perspective isn't about finding our smallness, but recognizing our belonging to something grand. Curiosity emerges as our defining trait in this vastness. Other animals build nests or solve puzzles, but humans launch telescopes to study galaxy formation. We bury time capsules with hydrogen atom diagrams. We decode light from the cosmic microwave background like detectives reconstructing a crime scene. However brief our moment in cosmic time, we've spent it reaching for understanding. This brings us back to the anthropic principle. The universe's constants allow for observers like us to change the strength of gravity slightly, tweak the nuclear forces, and stars might not form or life might never arise. But is this profound or tautological? We can only observe a universe capable of producing observers. It's like a puddle marveling that its hole fits it perfectly. The cosmic perspective offers comfort in its indifference. The universe doesn't care about humanity, but that very absence of care grants us freedom. There's no script, no predetermined role. We decide what matters locally while drifting on a tiny rock through vastness. The stars will continue their cycles whether we watch them or not. Carl Sagan's reflection on the pale blue dot, how everyone we know exists on that speck captures this duality. Universe dwarfs us, yet we're the part that notices. When physicists study quantum mechanics or poets write about the night sky, they're exploring the same fundamental wonder from different angles. That wonder might be the point. If the universe has any intrinsic purpose beyond its physical laws, it's hard to discern. But purpose isn't something found like a rock. It's built like a telescope. We assemble meaning from what we discover. The atoms in our brains, forged in stars, now arrange themselves into patterns that question their own existence. That recursive loop, the universe contemplating itself, might be purpose enough. Our cosmic journey reveals practical limits. Though however grand our perspective, physical barriers constrain what we can know. The speed of light creates horizons we can't cross. Dark energy pulls galaxies away faster than we can reach them. The universe's earliest moments remain obscured by primordial plasma. Some answers might always hover just beyond our grasp as we approach those ultimate boundaries. Between knowable and unknowable, we encounter perhaps the strangest realization of all. The same laws that prevent us from seeing the universe's edge or understanding dark energy also enabled our existence. The limits aren't arbitrary, they're the necessary conditions for everything we've explored so far. We bump against horizons, because horizons define the playing field where stars, planets, and life can emerge. The cosmic perspective ultimately circles back to Earth. However much we learn about distant galaxies, we still wake up to familiar sunlight each morning. When we discuss infinities and heat death, we do so while eating breakfast in finite lives. The grandeur of cosmology exists alongside mundane human moments, which might be the most extraordinary thing about us. The universe contains black holes. And supernova? Yes. But also creatures who paint landscapes and write songs about both. This leaves us with a quiet revelation. The universe's edge isn't the final frontier. Our expanding vision keeps pushing boundaries further out. The more we learn, the more questions arise. And that's okay, it means the cosmos keeps surprising us. Among all the possible cosmic outcomes predicted by physics, few could have anticipated something as wonderfully strange as beings who study physics. But even our grandest theories have limits. Some cosmic questions might remain unanswered, not because we lack imagination, but because the universe itself prevents certain knowledge. As we'll see next, the nature of reality may impose fundamental constraints on what we can ever understand about existence. Some mysteries might remain permanently beyond our reach, not unlike distant galaxies already receding beyond visibility. Here. It's the universe we can see galaxies, stars, and the faint glow of the Big Bang's afterglow. But what lies beyond our cosmic horizon remains a mystery, not because we lack curiosity, but because the laws of physics themselves impose limits on what we can know. Light's finite speed means we can only observe parts of the universe where photons have had time to reach us, yet space expands steadily, carrying some galaxies beyond visibility forever. No telescope, no matter how advanced, will ever catch their light. Some questions might never have answers. What happened before the Big Bang? Does the universe extend infinitely beyond what we see? Is ours the only universe, or one bubble in a sprawling multiverse? These aren't just gaps in current knowledge, they could be permanent blind spots. The inflationary period moments after the Big Bang erased evidence of anything that came before, stretching space so violently that earlier history grew inaccessible. Even light from that era can't reach us, meaning the universe's first instants remain hidden behind a veil of scattering particles. You might wonder why not just build bigger instruments? Surely a powerful enough telescope could glimpse further. But the problem isn't just distance. The fabric of space itself stretches faster than light can traverse it in some regions. Galaxies beyond a certain point recede faster than their photons can fight the cosmic expansion to reach us. It's like an ant crawling across an inflating balloon, no matter how fast it moves. Parts of the surface stretch away quicker than it can crawl toward them. The cosmic microwave background gives us our earliest snapshot, but it's not the beginning. That faint glow emerged 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. Before that, photons couldn't propagate without constantly colliding with charged particles, meaning we have no direct window into the universe's fiery infancy. Probing earlier requires indirect methods. Like gravitational waves from cosmic inflation, they even left detectable traces. Even our understanding of dark energy hints at unanswerable questions. Is it truly constant? Or could it evolve unpredictably? Right now it appears uniform across space, but we can't observe most of the universe to check. If dark energy varies in ways we can't see, our predictions about the cosmos's fate could be entirely wrong. And since we don't understand dark energy's origins, we can't rule out surprises. Consider parallel universes, regions of space forever, disconnected from ours due to cosmic expansion. If other bubble universes exist within a larger multiverse, we'd never detect them. Space's expansion rate ensures no signal from outside our observable universe could ever breach the growing void between us. The idea isn't necessarily science fiction, it emerges from plausible cosmological models, but it remains untestable by definition. Quantum mechanics adds deeper uncertainty. At the smallest scales, particles behave unpredictably, existing in probability clouds rather than fixed locations. Some theories suggest space-time itself. It might be quantized, composed of indivisible fragments, but these hypothetical space-time atoms would be unimaginably tiny, beyond any conceivable microscope. If true, the smooth universe we perceive would be an illusion, like mistaking pixels for continuous brushstrokes in a painting. Another unsolved riddle hinges on dimensionality. String theory proposes extra spatial dimensions curled into sizes smaller than atoms. They exist, we'd never perceive them directly, like ants unaware of the third dimension as they crawl along a wire. Even verifying their existence might require energy levels impossible to achieve in particle colliders. Some aspects of reality might simply be too small or hidden for human observation. Physics itself imposes deeper mysteries. Why do fundamental constants have the precise values they do? The strength of gravity, the mass of electrons, the speed of light tweak any, and life might not exist. Some chalk this up to the anthropic principle. We observe these values because they allow observers to exist. But whether that's a coincidence, a necessity, or evidence of a deeper structure eludes us. The nature of time presents yet another enigma. Why does it flow irreversibly? Laws of physics work equally well backward or forward, yet entropy always increases, creating an arrow of time. Was time's direction set at the Big Bang? Could other universes have time flowing differently? Answering demands knowledge of the singularity itself, information likely lost forever. Even within our observable universe, horizons exist. Black holes conceal singularities behind event horizons where normal physics breaks down. Information entering a black hole might be destroyed, violating quantum mechanics or stored somehow on the event. Horizon surface, as holographic theory suggests. We don't know which is true, and falling into a check isn't an experiment. Anyone survives to report. Some scientists argue that asking what's beyond the universe. If space-time began at the Big Bang, there might be no outside to speak of, just as there's no direction you can point from Earth's surface to indicate where the planet began. The question assumes space sits within a larger container, which may not apply. Others wonder if consciousness affects reality not mystically, but via quantum observation effects where measurements influence outcomes. Could the universe require observers to define its properties? If so, does that mean something fundamentally different exists in unobserved regions? These ideas flirt with philosophy more than testable science. Despite these limits, wonder persists. Mystery doesn't frustrate science, it drives inquiry. Every answered question reveals new unknowns, like turning a corner only to find more path ahead. The Hubble Space Telescope expanded our cosmic vision. Its deepest images raised questions no one had thought to ask. Technology extends boundaries, but can't remove them. Future telescopes might map dark matter structure or detect primordial gravitational waves. But they'll never show us galaxies already receding beyond visibility. Some cosmic eras left no trace, their stories lost to time. This isn't failure, but perspective. Understanding what we can't know defines science as much as discovering what we can. The universe owes us no explanations. Every glimpse is a gift. Our role isn't to unveil all mysteries, but to appreciate those we're privileged to explore. Perhaps the most human response to these limits isn't frustration, but inspiration. We ask these questions at all that Stardust can ponder. Its origins remains the deepest wonder. Scientific knowledge grows at the edges of uncertainty, where known meets unknown, and curiosity thrives. The cosmic horizon isn't just a boundary of sight, it's a frontier of thought, as we've traced, from Earth to stars, to the universe's observable edge. One truth endures. The more we learn, the vaster the humility and awe. Proving wonder doesn't require answers. Sometimes the question alone is enough now. Summing up, the universe's edge isn't a place, but a shifting limit of vision. From cosmic expansion to quantum uncertainty, our reach exceeds our grasp hand. That's okay. The night sky reminds us of both how much we've learned and how much remains hidden. In the end, the journey matters more than the destination. Look up tonight. You're seeing history, mystery, and the endless possibility of the unknowable. So we've traveled to what we call the edge of the universe, only to find it's not an edge at all, just the limit of what we can see. Each new horizon we reach reveals more questions, more mystery. That's the beauty of it. Carl Sagan said we're made of star stuff, contemplating the stars. That's really what this is, the universe trying to understand itself through us. The more we learn, the bigger the questions grow. So keep looking up. Wonder remains in the unknown, and the night sky will always have secrets waiting. Thanks for joining me tonight. Sleep well.